Hello everyone. We're going to do a review for the final over some of the earlier topics 1 through 4. This is not going to cover every single topic that we learned in 1 through 4, but should hit on most of the key elements, and I'll go through some examples that I think will demonstrate each of the main concepts that you guys need to know, and especially try to cover some topics that people seem to have trouble with along the way. So starting with topic 1, here's just a list of the different topics that will be covered. These can be found on the list of topics for the final that's on Canvas already. These are things that you probably learned in Organic 1 or perhaps even earlier on in Gen Chem. These are some ideas that we use regularly, like formal charge, hybridization, molecular orbital theory, electronegativity, resonance, aromaticity, recognizing electrophiles and nucleophiles, and also some acid-base chemistry. So I'm not going to do a whole lot of acid-base chemistry in this final review. I'm going to have a separate video that covers acid-base chemistry with a number of examples that'll highlight each of these concepts and how electronegativity, S character, and resonance impact the acidity or basicity of a molecule. There are also a variety of reactions that we also use fairly frequently in this class. These are SN1, SN2, your elimination reactions, different types of olefin addition reactions, and a few radical reactions. These are summarized in a handout I've posted. I made a summary of the different reactions from the early topics, including some of these ones from Organic 1, and that also can be found in the final folder on Canvas. So the first example I want to go through is just the idea of orbitals. So we talk about orbitals on almost every single exam or problem set. Usually this is in the context of a reaction. So in this case, the first part of any of these examples would be recognizing what type of orbital it is. So we can see that in this case we have two orbitals. These have pi symmetry, but we notice that we have two nodes going through the two orbitals, and this makes it a pi star orbital. So cases where we may want to think about a pi star is in later topics, for instance, the reactivity of carbonyl compounds. And so whenever we have a nucleophile added into something like a carbonyl, any reaction that takes place in pretty much any reaction that takes place, whether it's in this class or elsewhere, can actually be viewed as the combination or interaction of two orbitals. And there's always a filled orbital and an unfilled orbital. In this case, our nucleophile has all of the electrons. This is the filled orbital. It's also called the highest occupied molecular orbital. And this is a lone pair that is attacking the carbonyl as shown. Whenever we have a carbonyl attack, we can draw an arrow. We can draw the nucleophile making a bond to the carbonyl carbon. We end up breaking the pi bond and we make an alkoxide. So since this pi bond broke, this means the nucleophile was interacting with the pi star orbital, which looks roughly like the picture above. And along the way we see that the pi bond breaks. So a good way to recognize what orbitals are interacting, to say solve a question like this, we want to identify what type of orbital it's starting from. So in this case the nucleophile is a lone pair. This is referred to as N. We can be more specific, say it's N of a nucleophile. This could be an atom if we had a more concrete example. And the pi star would be a carbon-oxygen double bond. So we want to describe this entire reaction. We could say that this is the interaction of a lone pair from a nucleophile adding into the pi star of a carbon-oxygen bond. So if you can identify where the electrons start, what type of orbital that is, it could be a lone pair, it could be a sigma bond, or it could be a pi bond. It will always interact with an unfilled orbital. This will always be an anti-bonding orbital or a LUMO. And this could be either just an empty p orbital, a sigma star if a sigma bond is breaking, or a pi star in this case because a pi bond is breaking. So acidity is one of the key concepts, and I mentioned we'll have more discussion on this in another video. But just to sort of illustrate one of the, I think, elements that we brought in early in this class that I think comes up almost every single topic. This has to do with why a benzene CH bond ends up being much more acidic than, say, the CH bond in a molecule like ethane. So when we consider the acidity of some molecule, frequently we want to imagine what would the conjugate acid or base looks like. So if we are talking about acidity, we can go and imagine each of these were deprotonated and try to figure out what are the stabilizing factors that are present in each molecule. So if we deprotonate both ethane or benzene, we get an aryl anion or an alkyl anion. And a key thing to note is that resonance is not part of the reason why a benzene ring is more acidic, or a benzene carbon-hydrogen bond is more acidic than a CH bond in ethane. This really comes down to it having more S character. So this anion is located on an sp2 hybridized carbon, whereas ethane would be sp3. When we think about the atomic makeup of an atom, if we think about where s orbitals are spherical. Their highest density of highest electron density or probability of finding an electron in an s orbital is right in the middle, and this is where the nucleus is. If we consider a p orbital, there's actually going to be a node going right through the middle where there is no probability of finding an electron. So when we consider things like sp hybrids, the picture is somewhere in between these two. So something that has more s character or more percentage s orbital character, such as sp2, which is 1/3 s character, whereas sp3 is 1/4. We can also say that there's more electron density around the nucleus. And inside the nucleus, this is where the protons are located. Protons are positively charged, so they're going to be much better at stabilizing electrons and lowering their energy along the way. So again, resonance is not at all involved. All of the p orbitals are orthogonal to where this lone pair is. It's sticking out along the edge where the pi orbitals are above and below. And this is one of the key ideas that we use quite frequently. Now we're moving on to the idea of what is a nucleophile, what is an electrophile. So we talk about this pretty casually throughout the class. And in this set of examples, we need to consider usually what is a nucleophile. Usually when we think of nucleophiles, there's electrons that have high energy that want to go and react with something. So the quick way to answer this question from these given molecules is we can go see that this nitrogen has a lone pair. We see that this thiophenolate anion is negatively charged, and so it will certainly be nucleophilic. Usually things that are negatively charged are better nucleophiles. We have an aromatic ring, which isn't necessarily always the best electrophile, but it does have this O-methoxy on it. And when we get to topic 2, we find that these are electron donating groups, and these will increase the nucleophilicity of a benzene ring. Now we see that we have an enolate, and we know these are good nucleophiles. Again, they have a negative charge on the oxygen. These end up being nucleophilic at carbon. And the last one is this oxocarbenium. So the positive charge is the big giveaway if you just quickly want to answer the question, that this certainly will not likely be a nucleophile. There is still one more lone pair on this oxygen, but it already has a positive charge on it, so it's holding on to those electrons very tightly. And so this would be much better described as an electrophile. And we know that all the reactions that take place are as an electrophile in this class, where we could have a nucleophile and it would be attacking that carbon-oxygen bond. So if you look back at some of the earlier examples, you'll see that some of these molecules that we were analyzing at the beginning of the class, we've now seen in practice much more towards the end. This is a problem that I think was on one of the problem sets, and it just goes through ranking these different protons from most acidic to, or from least acidic to most acidic. So now with a bit more, I think, knowledge and familiarity with these different functional groups, this one might become a bit more straightforward. We still have our pKa's to fall back on, and going and looking at the pKa table is actually pretty useful. And I think we kind of have analogies from each of these, or almost each of these, for different pKa's we're supposed to kind of have on hand to remember. So if we see a carboxylic acid, we should be thinking, okay, this is going to have a pKa of around 5. 4.8 is what we have listed, but if you get to the nearest whole number, that is always going to be okay for this class. If we have an alcohol, we know this is going to have a pKa of about 16. Substituents on the alcohol do change its magnitude a bit, but we can say about 16. We have this alkyne, so we can go to reference of ethyne or ethylene, and its pKa is about 25. And really the only one we do not know or have designated in our memory bank, at least that I've requested, would be HB. And this is just a normal CH bond. And so I would hope you could imagine that a deprotonating this hydrogen, making a tertiary anion, is going to be highly unstable, particularly relative to the conjugate bases of a carboxylic acid, which allows the electron density to go and flow between two oxygen atoms. Oxygens are very electronegative. The oxygen to the alkoxide would also be much better at stabilizing. And here we also have the difference between an sp carbon and an sp3 carbon. So even if we don't know the exact pKa of HB, we know that it's going to be super duper duper high. In actuality, this one is, we can probably say more than 50 for its pKa pretty safely without any extra information. And it would be useful to always go back to rely on some of these pKa's that we should have memorized and be familiar with to more quickly analyze problems like this. So this next question is asking, which of the following is not a Lewis acid? So a Lewis acid is something that wants to take electrons. You could also phrase this as what is not electrophilic. And as we go through, we need to look at the structure, or at least try to make some analogy of how we've used these types of reagents in the class. If you consider the structure of BF3, boron itself is electron deficient. It's actually a 6-electron species. So it has this empty p orbital that will be very electrophilic. For alane, aluminum trihydride, aluminum is just one element below boron on the periodic table. It also is electron deficient and has an empty p orbital. The methyl carbocation, once again, is electron deficient, and all of these are isoelectronic with one another. So we know this definitely wants to have electrons around. Now that carbon's lost its octet, we put a positive charge on it. If you go to iron trichloride, it's a little harder to consider its structure to start predicting the reactivity implicitly, but we do have a transition metal with 3 chlorides. The chlorides are fairly electronegative. We've also seen this in the context of the Friedel-Crafts reaction. And its role in Friedel-Crafts reaction is actually to go and react with chlorine to further activate it. In the process, iron actually takes the electrons from chlorine to make the activated iron trichloride complex, where we end up making chlorine even more electrophilic. So this is a case where probably the easiest way to identify this is to think about where have we seen this reagent and how was it used. The last example is dimethyl sulfide. So dimethyl sulfide doesn't really have any electrophilic groups. It has two orbitals or two lone pairs on the sulfur. So the closest analog we may have is something like an alcohol or an ether, and alcohols are frequently being used as nucleophiles. So there's no way for this to really accept any more electrons. So if nothing else, through a process of elimination, we can arrive at dimethyl sulfide not being a Lewis acid, and this really would be a Lewis base because it has lone pairs that it can go and give to someone else. Someone if molecules are people. Next is a hybridization question. And this is one of the key ones where we're going to have a heteroatom like oxygen. Both oxygen and nitrogen can have variable hybridizations. You can't rely purely on the number of bonds it has. We need to go look a little bit more closely at its structure. So the main feature of furan is that it is aromatic. So it's in a 6-electron, has a 6-electron pi system. So one of these electrons is actually lone pairs of the electrons is turned into a purely p orbital in order to make it aromatic. So I'm going to attempt to draw this a little bit more in a perspective sense. I'm never terribly good at this. But we're going to end up with one of the lone pairs kind of sticking out directly away from the ring, and another one will be directly above and below the ring. This orbital that is now above and below will allow it to communicate with all the other p orbitals in the pi system to really give it aromaticity. If you're ever trying to determine is a heteroatom like an oxygen or a nitrogen sp3 or sp2, one of the big key giveaways is that there's going to be some sort of double bond next to it. So something like the nitrogen in an amide is sp2 because it is using these electrons to resonate with the neighboring pi system. And that usually will answer the question pretty quickly. The case of furan is somewhat unique in that it has one lone pair that is in the pi system and another lone pair that is not in the pi system. And so this would leave this as being sp2 hybridized. We'll circle an answer. All right, now we're going to move on to topic 2. This is where we had all the reactions of aromatic rings. So we learned a wide range of electrophilic aromatic substitution reactions. We talked a lot about the rhenium intermediates, what's an orthopara versus metadirector, activating, deactivating substituents, etc. We learned a variety of side reactions, things how we have a special reaction to reduce aryl ketones and aldehydes to methylenes. This note is only useful on aromatic carbonyl compounds. If you have an aliphatic carbonyl compound, you want to use the Wolff-Kishner reaction, though the Wolff-Kishner reaction will also work for these aromatic carbonyls as well. The other thing to note is does not work on carboxylic acids. There's a variety of side chain reactions such as oxidation with radical chemistry or potassium permanganate. We now have actually a lot of different ways to reduce nitro compounds. When you reduce them, they turn into anilines. We had more chemistry of diazonium salts that now come from anilines that we can make. We learned the Claisen rearrangement, which was this fairly maybe out of character for this topic, but it does use aromatic rings. That will let you use a cyclic transition state, and after tautomerization of the intermediate phenol, it can move an allyl group from the oxygen to the carbon. And lastly, we learned two other types of aromatic substitution that were based off of nucleophiles or strong bases, which are also nucleophiles in those reactions. And those are with nucleophilic aromatic substitution and benzynes. So we're going to do a case from a couple of these just to remember different factors and how they work. In this case, we have the combination of a benzene ring. We have aluminum trichloride and an alkyl halide. This is the Friedel-Crafts alkylation. And to determine the product, we need to remember how this reaction goes. So the first thing that happens is we have the alkyl chloride, and we have aluminum trichloride. So aluminum trichloride is a good Lewis acid. It's going to go and essentially make a bond with chlorine. It's going to try to rip this chlorine off. Depending on the situation, we will go and take this all the way to make a carbocation. So this allows us to go and make a very stable tetrachloroaluminate anion and this primary carbocation. So primary carbocations are not stable. They always want to rearrange. The bond that migrates could be a hydrogen or a carbon, and the one that migrates is the one that will end up giving you the more stable carbocation. So we'd expect to have a 1-2 shift. This will give us a tertiary carbocation, and this is going to be our actual electrophile in the reaction. After that intramolecular reaction takes place, we're able to have benzene attack the tertiary carbocation. This gives us an rhenium intermediate, and we didn't have any substituents on the rhenium this time, so we didn't have to worry about where it goes. Note that the rhenium is stabilized by putting that charge on several carbons. So a lot of times you can see these rheniums looking almost like they're delocalized with a positive charge kind of shared across these three alternating carbons. In the end, your tetrachloroaluminate can come back, give up its chloride, and we will remake the aromatic system. And we'd end up with a tert-butyl group. So this would give us C as the expected product. So carbocations are something you always want to be looking out for. If we know the mechanism and know whether it goes through a carbocation or not, we'll know whether to expect a rearrangement. This next question is asking, which would react the fastest with bromine and water? So actually there's only two different aromatic compounds we learned that do react with bromine and water without any added Lewis acids. And that ends up being phenol and aniline. So if you know that, then you already have your answer. It's A. But if we wanted to go and kind of rationalize this a bit more, how do we know what would react fastest? We do have bromine as the electrophile. So we want to figure out which one of these benzene rings is the most electron rich. So we need to be able to identify what are these different substituents. Are they going to be electron donating groups? Will they be activating groups? Or will they be electron withdrawing groups? The nitro group is our strongest electron withdrawing group. If you look at the nitro a little closer, it even has a positive charge on that nitrogen. So this ends up being very strongly electron withdrawing. A methyl is a mild electron donating group. The iodide and the other halogens These are ortho-para-directors, but they are mildly deactivating. So this means that overall, the electron density decreases because of the electronegativity of the halide, but they still have lone pairs that, if they're forced to react, will go and participate in the selectivity of the substitution. The last two to compare are the aniline and the anisole, this methoxybenzene derivative. The lone pairs on both oxygens and nitrogens are pretty happy to be shared across different pi systems, and they'll go to stabilize an rhenium. So if we imagine having a reaction take place, the rhenium doesn't put the positive charge directly onto the benzene ring. It can actually shift it over to these heteroatoms. And this is stable. This is a good thing because we can make a full octet. And this leads to them being very good electron donating groups, very strong electron donating groups. To decide which one is going to be more electron donating, we're going to go and take one other factor into consideration, and that is electronegativity. Oxygen is more electronegative, so it doesn't really want to put a positive charge on the oxygen as much as a nitrogen would. Nitrogen will end up being a much better electron donating group. So even though oxygen is pretty good, the aniline series will be much better. Oh, I copy and pasted the same slide twice. The answer's A. So now we're switching gears and we're getting out of the electrophilic aromatic substitution and we're moving to nucleophilic aromatic substitution. So this uses the same sort of logic, only now we're trying to stabilize negative charge instead of positive charge. So we're going to have a benzene ring, try to substitute a leaving group, and we know that if we have a nucleophile attacking a benzene ring, if it's a substitution, it'll have to attack the same carbon as the leaving group, and that'll cause the benzene ring to dearomatize. So whereas the uranium ion has a positive charge, this is the same thing, only we're putting a negative charge in that dearomatized system. Similarly, you can go and put this charge on any 3 carbons, and this is the same sort of ortho-para relationship, ortho-para-meta considerations we kind of borrow over as well. And you could also put it on this last carbon. So in order to stabilize a carbon ion, we want to have now an electron withdrawing group. These will be the best at stabilizing negative charge. When we look at all the different options, all of these have one thing in common. Each one has a nitro group, and these are strong electron withdrawing groups, so this is going to be good. And they also all have a leaving group of some sort of halogen that potentially could leave. So the thing we want to do is put this negative charge on a carbon that has that electron withdrawing group. So if you imagine that I'm going to copy and paste this. So let's imagine we had a nitro group in this place, in the 2 position, for instance. You'll see that we'll be able to use resonance to go and put the charge all the way onto an oxygen. So having the electron withdrawing group, especially one that has resonance stabilization like a nitro or some sort of carbonyl, is very important for this reaction to take place. The slow step, similarly, is going to be the addition to break aromaticity, so there really needs to be a really nice stabilizing group in order for that to occur. If you go and look at where the charge ends up going on the benzene ring, we'll see it's here, here, and here. So it's ortho and para. That means on the starting molecule, we want to have that electron withdrawing group in the ortho or para position. So based off of that, we can say that B, C, and E are not going to be good options. Even though they have nitros, and E even has 2 nitro groups, they're not going to have the same stability because they're in the wrong position. They'll have inductive stabilization, but that's not enough in order to break aromaticity. You really need to be able to make a resonance structure. So this gives us 2 different options. We have A, or we have D. And this is also where the logic of how these reactions works kind of gets a little bit backwards. Normally you think about iodine being a good leaving group. But in this case, the step in which these molecules leave is actually quite fast. This ends up being the fast step, is the lone pair coming back and kicking out the leaving group. Since the slow step ends up being the de-aromatization or the initial attack of the nucleophile, the most electronegative leaving group ends up accelerating the reaction most. So we're looking for what's fastest. We have fluorine that is much more electronegative than iodine. It will end up further polarizing this carbon for attack of a nucleophile. It has the nitro group in the ortho position that will further stabilize that intermediate. So A ends up being our best option for nucleophilic aromatic substitution. Ooh, 10. This might have been one of the problems from an exam, I think. But I think we had a practice problem that was somewhat similar. So now we have a very, very strong base. We have sodium amide, and that is the key giveaway in this problem. We only use sodium amide for a handful of things. Sometimes it's a very good base to deprotonate something, and in this case, really is no different. But whenever we have sodium amide and combined with some sort of benzene ring that has a halogen on it, this is going to tell us that we are going to make a benzyne. So the way this works is you have the sodium amide. It actually has 2 different options. It could either attack this hydrogen, or it could also attack the hydrogen on the other side. I'll draw both of these out below. So we're going to make an aryl anion, which is normally something you wouldn't be able to do. It's facilitated slightly by the chlorine that is neighboring. The chlorine will inductively lower the pK of that hydrogen enough so that you can get some of that sodium amide deprotonating it. This is a 2-step process. You do make an aryl anion first in the mechanism. After you make the aryl anion, then you get the elimination to make benzyne. And this involves arrows, as you would imagine. The lone pair comes down, kicking out the chloride. And now we get 2 different types of benzynes from the same intermediate. So I'll draw these out. So there's a lot of resonance structures you can draw of benzynes. And if you draw out these resonance structures, then you will see that they can actually be attacked at either position of the carbon. This is because these are both valid resonance isomers of benzyne with these positive and negatives And you can actually move these to either spot. All of these are valid. So actually both of these carbons are fairly electrophilic. Afterwards, you have these very strong amide bases still in solution. So not only are these very good bases, but they are also very good nucleophiles. And so this has the option of actually also attacking either one of these carbon atoms. Again, this sodium amide also has the option to attack either one of these carbon atoms. So from each of these benzynes, we're going to go and make 2 different products. So this gets perhaps fairly busy. After it attacks across the alkyne, you'll make an aryl anion, and that aryl anion will deprotonate the ammonia that's in solution. So I'm going to just draw the products. Hopefully you can imagine that protonation taking place. So if it attacks the top carbon, we're going to make this aniline product. If it attacked that lower carbon, we would end up making this aniline product. Now we go to the other potential benzyne. This could attack its relative top molecule. And you'll notice that we probably don't even need to draw out another structure. It's going to go to the exact same one again. But if it attacks the lower carbon, we will in fact make a unique product distinct from the other two. And these are the 3 options of what you hypothetically could make. So we could see that A, we are making. We never are able to ever make B though. B is inaccessible. And we'll talk about maybe in a bigger picture why that is pretty soon. We see that we made C, we made D. So maybe a faster way of looking at this is, instead of going through all of these different mechanisms, if you know that you can make a benzyne from either side of the leaving group, that means that all 3 of these positions surrounding the halide can be substituted. If it's not directly adjacent to the halide, that means that a benzyne would never form there because you never could eliminate to make it.